All right, hey geometry class. This is going to be our lesson on 5.3, use angle bisectors of triangles. So this is going to compare back to our last lesson on perpendicular bisectors. Instead of splitting segments in half, we are going to be splitting angles in half. So, and we're going to be doing that with triangles. So our objective in this lesson is we're going to be mainly applying theorems about angle bisectors. All right, so here are some angle bisectors theorems. And here's what an angle bisector is. Here you see that we have an angle APB, and there is a ray going through it. So PC, that ray going through our angle, is the angle bisector. And the reason I say it's the angle bisector is because it's showing that this angle and this angle are congruent by those two markings. So PC is splitting APB in half. Okay, so that PC is the angle bisector of that angle APB. All right, let's look at these theorems. The angle bisector theorem, it says if a point is on the bisector, so referring to this point right here, point C is on the bisector of an angle, then it is equidistant from the sides of the angle. Okay, so C, then straight over to this side of the angle, PA, we're going to be, how you know it's straight over to it is it's going to be intersecting, this line right here is always going to intersect this other angle, part of the angle, with perpendicularly. That's what I was trying to get out, at a right angle. And same thing goes with this one. From this point C straight down and it's going to intersect this side of the angle perpendicularly. These two segments, AC and CB, are going to be equal to each other. That's what the conclusion states right here. AC is equal to BC. Okay, and that only happens whenever we know that we do have our angle is being split in half. We have an angle bisector. Okay, so let's look at the converse of this. So if we know, let's not read this. Let's look at this picture right here. If we know that this segment that is on this line right here, this ray, is congruent, if AC is congruent to CB, then we should know that angle APC and BPC are congruent to each other, meaning we know that PC is the angle bisector of APB. All right, so in this first example, it deals with what we just looked at, the angle bisector theorem and its converse. And we're asked to find this measure. We're asked to find the measure of BC. Over here, BC is this segment right here. And we know that AC is the angle bisector of BAD. So, we should know by that angle bisector theorem that these two segments are congruent to each other. So this means that segment BC is equal to 7.2. Okay, so there we have it. For our next exercise, we are going to be looking at using or applying the converse of the angle bisector theorem. So let's take a look at this. It says find the measure of this right here, measure of angle EFH, given that um, measure of EFG is 50 degrees. So what we're looking for, EFH, is this angle right here. And we know that FH is the angle bisector because all of this given information in the picture here shows us that um, this segment EH and GH are congruent to each other. So therefore, these angles right here are congruent to each other. And if these two angles are congruent to each other, then how we're going to find EFH is by saying, well, EFG divided by 2. And we are given that EFG is 50 degrees. So the measure of angle EFH is equal to 50 divided by 2. I'm going to go ahead and write that out. 50 divided by 2. Because we are splitting that in half. And so that is going to give us 25 degrees. And we're done with that one. Okay, here we are given, again, we're going to be using the converse of the angle bisector theorem. We are given that JM is congruent to ML, and that means that these two angles right here and here are congruent to each other. So before we go and find the measure of MLK, which is this one right here, that's the one that's in question, we need to figure out what A is equal to. Since these angles are congruent to each other, then we can set the 3A plus 20 equal to 2A plus 26 and have an equation to solve. So 2A plus 26 is equal to 3A plus 20. All right, so solve this one. We get, subtract 2A from both sides, you get A. Subtract the 20 from both sides, you get 6 over here. So A is equal to 6. Now take your value of A and plug it back in to actually either one of these. We're going to get the same measurement because these angles are congruent to each other. But plug your A back into where it's supposed to go, and the measure of angle MKL is equal to, I'm going to go ahead and plug it in like this, 2 times 6 plus 26 degrees. And that is equal to, let's see, 38 degrees. And we're done. All right, so now that we know a little bit more about angle bisectors, let's look at angle bisectors and triangles. A triangle has 3 angle bisectors. So there are some properties about angle bisectors in a triangle, just like there were with the perpendicular bisectors of all 3 sides of a triangle. It had a point of concurrency. So does this one. The angle bisectors of a triangle are concurrent, as you can see in this picture right here. All these lines that are in red are the angle bisectors, and they intersect at this point P right here, which is called the incenter of the triangle. And the thing about an incenter here, the incenter of a triangle is equidistant from the sides of the triangle. Remember what equidistant means from a point to a segment is we draw a line that from that point perpendicular to that segment That is the distance between a point and a line segment, is you have to draw it perpendicular to that line segment. Okay, so all three of these distances from P are going to be equal to each other. That's what the in-center theorem is. Okay, unlike the circumcenter, the in-center is always going to be on the inside of the triangle. Remember in the last lesson, we saw that acute triangles, all the angle bisectors, they came together, and the circumcenter was on the inside, and then the obtuse triangle is on the outside, and then the right triangle is on the triangle. Well, in this case, the in-center is always going to be on the inside of all types of triangles, just like you see in these pictures. Another thing about the in-center is the center of the triangle's inscribed circle, just like the circumcenter was the center of the circumscribed circle of a polygon. This circle can be inscribed inside the polygon, and for it to be inscribed in the polygon, using this point right here, it's going to touch all three sides of the triangle. I mean, just touch it. It's not going to go through it at all. It's going to touch each side of the triangle, just like this does right here. And that is what inscribed circle is of a polygon. All right, so let's look at this example. We're going to be using properties of angle bisectors of triangles to help us figure out some distances and angle measurements. All right, so it tells us that MP and LP are angle bisectors of triangle LMN. First, we're going to find the distance from P to MN. Then we're going to find the measure of angle PMN. Let's find the distance first from P to MN. And remember, the distance from a point to a line segment is going to be perpendicular to that line segment. So let's try to draw that in. So from point P, that's terrible. Let me try that again. There we go. It's a little better. Okay. And there's my right angle. Okay. Just like the the in-center theorem stated, all of the distances from the in-center to the segments of each side of the triangle are going to be equidistant. So this segment right here is congruent to that segment there. And I'm going to call this, I'm going to give that a letter O. And I'm going to say that's the distance that we are looking for. OP is equal to 5. So that answers this question that we just looked at. Find the distance from P to MN. So the distance OP is equal to 5. All right, now let's look at finding the measure of PMN. So PMN, this angle right here is what we're looking for. And now, let's see, LP is an angle bisector, and so is MP. That's what is stated up here. MP and LP are angle bisectors. So if we know that this angle over here, PLN, is 50 degrees, this right here is also going to be 50 degrees because they are congruent because of properties of angle bisectors. So in this triangle, remember triangles, all the angles inside a triangle add up to 180 degrees. So here's what I'm going to do. I'm going to write out that the measure of angle L plus the measure of angle M plus the measure of angle N, they all add up to 180 degrees. Now angle L, if we take 50 and add 50 again, that total angle measurement is 100 degrees. And then measure of angle M, well, that is kind of what we're looking for, at least the partial of it, half of it. So let's find what measure of angle M is. We know N is equal to 20. So let's plug in 20 degrees here. Now we have a little equation here. We can solve for the measure of angle M, and that is equal to 60 degrees. Now this angle over here, PMN, what we're looking for is half of angle M, because MP is the angle bisector. So measure of angle PMN is half of 60. So we get the answer 30. There we go. All right, so let's do another exercise that's similar to the last one. So we have QX and RX are angle bisectors of triangle PQR. Find the distance from X to PQ. Also find measure of angle PQX. All right, so here we go again. The distance from X to PQ. So this point right here, this point is the incenter. And to draw this from point P to PQ, it must be perpendicular to this. So there we go. And since this is showing that X to this segment right here, PR, is perpendicular, we can say that distance right there is congruent to this one here. So X, again, I'm going to label this O, is equal to 19.2. So XO is equal to 19.2. Now let's find the measure of PQX. And just like the last one, we are given some stuff, some angles here. We know this angle here and this one here are congruent. Sorry, having technical difficulties there. All right, so we have 12 degrees in here. And so the total measurement for angle R is 24 degrees. The angle measurement for P is 52. And so finally we're going to figure out what is the measurement for angle Q. And then from that, we can find the measure of PQX. All right, so measure of angle Q plus measure of angle P plus the measure of angle R is equal to 180 degrees. We don't know Q, that's what we're trying to figure out. And measure of P is 52 degrees. And the measure of R, total of 24 degrees. And again, it's equal to 180. Now the measure of angle Q, if we subtract 52 and 24 on both sides of that equation, we get 104 degrees. Now, this angle and this angle are congruent, and so we're going to say to get the measure of angle PQX, we're going to split this angle in half. So divide that by 2, and you've got what we're looking for, the measure of PQX. And that is going to be equal to 52 degrees. And we're done with that one. All right, in this example, we're going to be using this diagram here. It says in this diagram, N is the circumcenter of triangle ABC. Find ND. All right, let's talk our way through this one. ND is over here. And remember, if N is the incenter, all of these lines that you see in blue that have the right angle being shown, they are all equidistant to the sides of the triangle from N. So all of these are congruent to each other. So ND, NE, and NF are all equal to each other. So if we find the measure of one of these sides, then we know the measurement for all of these segments that I just named off. So that is going to help us in this right here. We have a little triangle. Let me highlight that one in a different color here. We have this triangle right here, and it's a right triangle. All right. So that right triangle right there, we have 16 and 20, and we don't know the other side. If we find what NF is equal to, then we know what ND is equal to. And how we're going to find this measurement in F is by the Pythagorean theorem. Now, I know y'all have studied the Pythagorean theorem at some point, but I'm going to remind you of that. That's what I'm here for. Oops. Go back. Let me get my other color back out. All right. So the Pythagorean theorem states this right here. A squared plus B squared equals C squared. And what A, B, and C are parts or all sides of the right triangle. A and B are the legs of the right triangle. It doesn't matter which one you put down as A and which one you put down as B. It's going to be the same. Well, they're not going to be the same. Answer's going to turn out to be the same thing. And the longest side of a right triangle is always the hypotenuse. And the hypotenuse is your C in this equation. So A, B, and C, let's fill those in with the names of this triangle right here. So NF is one of the legs. Let's put that in as A. NF squared plus B squared, which is AF, that's the other leg. And then C, our hypotenuse, that's AN. Now let's fill these in with numbers. NF, we do not know. So let's just keep it as NF squared plus AF is 16. Let's put that in, 16. AN we know is 20, and square that. Now let's do some calculations here. 20 squared and subtract 16 squared on both sides, we are going to get 144. Now take the square root of both sides to get NF alone, and we get NF is equal to 12. So now that we know NF is equal to 12, and we know that all of these distances are congruent to each other, then ND, what we are looking for, is also 12. And there we go. There's our answer. All right, so now it's y'all's turn to do this lesson quiz. And like we've been doing in class, we're going to do this at the very beginning of class and see how y'all understood everything. So do this portion on your own, and I will say on part 3, or question 3 here, that it's a lot like the last one we just did in this lesson. So if you want to go back and listen to me and do that one over again with me, do that to help you in finding the answer to this question here. So I will see you all in class. Goodbye, everybody.